Now that we have gone through the basics of rigid body mechanics, let's look at how that applies to the human body, specifically the arm. This drawing shows a simple version of an arm holding a weight. It is not super detailed, but it's enough to understand what's going on. First, we have the biceps, which is pulling upwards. That's the muscle responsible for folding everything up and keeping the arm steady. At the end of the arm, there's a dumbbell being held in the hand. It pulls down due to its weight. In this example, it's 20 kilograms, so not exactly light. We also have the forearm, which has its own weight too. It's easy to forget about, but it definitely adds to the load. We are using 2 kilograms for that, which is pretty average for an adult. Lastly, the elbow joint is acting as the pivot point. It's the spot everything is rotating around, even if the arm isn't actually moving. So this is the basic setup. We've got upward and downward forces acting on the arm. This helps us see how different parts of the body work together to keep things balanced. Alright, now let's talk about the distances between each of these forces and the pivot point, which is the elbow. The longest distance here is from the elbow to the dumbbell in the hand. That's the full length of the forearm, and in this example, it's about 40 centimeters. Since the dumbbell is so far from the pivot, it creates a lot of torque. Next is the forearm's own weight. It doesn't act at the end, it acts from the center of the forearm. So that distance is about 20 centimeters from the elbow, right in the middle between the elbow and the hand. And finally, the shortest distance is where the biceps pull. The tendon is attached just above the elbow, and in this case it's only about 4 centimeters away from the joint. These distances are super important because the further away a force is from the pivot, the more torque it creates. That's why even though the biceps are a strong muscle, they have to work really hard. They're pulling from a very short distance. Alright, so now that we know where all these forces are acting and why the distances matter, let's put some actual numbers to it. For our example, here's what we were working with. The dumbbell has a mass of 20 kilograms. Now, why is this force going downwards? Simple, because of gravity. Gravity always pulls things down towards the center of the earth. So any weight you hold or that your body has will exert a downward force. To turn that 20 kilograms mass into a force that we can use in our equation, we'll multiply by the acceleration due to gravity, which is about 9.81 meters per second squared. So 20 kilograms times 9.81 meters per second squared gives us the downward force from the dumbbell. The forearm has a mass of 2 kilograms. Just like the dumbbell, its weight is also pulling downwards due to gravity. We'll do the same thing here. 2 kilograms times 9.81 meters per second squared gives us the downward force from the forearm's own weight. The distance from the elbow to the dumbbell is 40 centimeters, or 0.4 meters, which is what we will use in our math to keep units consistent. This will be our D1. The distance from the elbow to the center of the forearm, where its weight acts, is 20 centimeters, or 0.2 meters. That will be our D2. And the distance from the elbow to where the biceps attach is a super short 4 centimeters, or 0.04 meters. This will be our D3. Now, you might be wondering, why are we even bothering to calculate the biceps force? Well, it's because of how our arm is structured. Our arm acts like a lever, and because the biceps muscle attaches so close to the elbow, it has a real disadvantage in the terms of leverage. This means the muscle actually has to pull much harder than the weight you're holding to keep everything balanced. It's not immediately obvious just by looking, so calculating it helps us understand the true forces involved in our body. When you set up our equation, we think about torques. Torques are like rotational pushes or pulls. We have two main types: clockwise torques, which are forces trying to make the arm rotate downwards, like the hands of a clock. In our case, both the dumbbell's weight and the forearm's own weight create clockwise torques. They are both pulling the arm down. And counterclockwise torques. This is the force trying to make the arm rotate upwards against the clock. The biceps muscle is doing this. It's pulling up to counteract the downward forces. For the arm to stay perfectly still, to be in equilibrium, all these torques have to balance out. So the total clockwise torque has to equal the total counterclockwise torque. That means our main equation will look like this. Dumbbell weight times D1 plus forearm weight times D2 minus bicep force times D3 is equal to 0. So, After simplifying, we get that 78.48 newtons plus 3.924 newtons divided by 0.04 meters gives us the biceps force, which after further simplification gives us 2060.1 newtons. That's a lot of force. So after all that calculation, we found that the force your biceps needs to generate is about 2060.1 newtons. Now, what does that number actually mean in a practical sense? Well, let's put it in perspective. The dumbbell you were holding had a mass of 20 kilograms, which translates to about 196.2 newtons of downward force due to gravity, but your biceps had to pull with over 10 times that amount of force internally. This illustrates a really important concept in human body mechanics, leverage. Because your biceps muscle attaches so close to the elbow, that short 4 centimeter distance, it operates at a mechanical disadvantage. To balance that much larger torques created by the dumbbell and even your forearm's own weight, which are acting much further away from the elbow, the biceps has to generate a disproportionately large force. It's working incredibly hard. Even with the weight you are holding externally seems manageable. To give you an idea of the magnitude, 2060.1 newtons of force would be the weight of an object with a mass of roughly 210 kilograms. That's the internal pull your muscle has to exert.